So we'll start now. So till now we've had a very detailed, very nice, the whole thing which Professor Nilias has talked about, the numerical computation, which many of us are trying to do, but I don't think so we are anywhere near to what Professor Nilias and his group has done, and I've been trying to follow that for some time. So for a slight change, and also because we have done a little bit more, I'm sure there's experiment done in Lyon also, but the experiments we've done in 1 hour, two kinds of contact analysis, experimental results for rolling sliding contact, which is for gears, ball bearings, roller bearings, and then fretting. Both are basically PhDs which have been done and papers have been published. So this is the first one where this is a rolling sliding fatigue study actually of a rail wheel contact. So the rail in India is made of paralytic steel. So that is now, so we don't have a rail, we don't have a wheel, but we have the material, and we have this tribometer in IIT Patna, which is a Plint TE74S, where I should have actually put some details on this. It can go to very high loading, and SRR we've seen with lubricated contacts, it can go to 30–40% also, maybe more. But dry, because the friction is so high, you can't go to, we'll show you what whether one study was done, because rail wheel contact is dry, is also wet with water, and now with snow, because we have some of our trains running in snow now in Jammu and Kashmir. So it can be both, at least with a focus on our development for the country. So running, we've tried to do some dry test also, rolling sliding, but that is like doing for a short time, stopping it, then lubricating it to cool it down, then remove the oil. So that is the way we could do it actually. Or you do pure rolling in dry condition, which doesn't satisfy the conditions of a rail wheel contact, because there is some sliding happening. So there are two aspects to the results which I'll just show you. This is the tribometer. I'll show you the results of this. Also abacus finite element modeling has been done. We've got these two rollers we've modeled. Similar, it's trying to compare this. Now, of course, the question which will come later, or you will all look at how much we could validate. Well, we could validate only one thing, the accumulation of strain. These elements here got compressed because of that. We'll show you. So, but the abacus and the analytical model, as has been shown till yesterday, Professor Nilias, that you can go to great depths. You can understand things which you can't measure in experiments, and that helps in the design, failure analysis, and other case studies. So if you see the rail wheel contact, there are lots of issues actually, and things like the spalling, especially. Let me tell you that these electric locomotives also have a case of fluting on the track, which is current also passes through, and that also, fluting is the term for the wear in bearings, because of, and gears also. In wind turbines, it's going through gears also, the current. So there is squat marks and rail burns. So we've got basically elliptic contact here, which we are trying to model on our abacus. You can model that, no issues, with a roller and roller, with a crowning on one roller. Now, crowning on one roller is to give you elliptic contact. It is also to avoid edge loading, which Professor Nilias showed. Otherwise, you will have just two marks, or two lines, as we were seeing on a circle there. You will get that, and it's of you won't get the pressure at the contact area. So that's why, which was explained very well, for roller bearings also you have the logarithmic profile. So here we've done crowning. So this is a paper, of course, which was been published in Forces in Mechanical Engineering. So now there are two parts to this. This is the abacus modeling actually. So we've done for a different amount of slide, okay, in abacus. So now we'll see the problem with abacus. It takes a long time. We saw that also. So we did just 10 rounds of these rollers, which took about 2 to 3 days, and but we could get a lot of results, especially on the plastic deformation, which you will just see. So the model is 2D plane strain finite element model. It's a 2D model. Center of the disc, center of can move along radial direction, just like it can move in the rig also. Here we have applied 11.2 kilonewtons, which is a very high load. The rig can go up till 12 kilonewtons. All this is just finite element just now. Now we've got the kinematic hardening model, which we've used here, which was also so we've used that. Now the values for this kinematic this thing have to be either from literature, or you measure it through a tensile test setup. Okay, these values you will get for that particular material. We've got it from literature. So we've got these the abacus model. You can see that just like we saw it before also, the elements at the contact have to be really fine. Okay, and the mu we've taken it to be 0.35. You see, this is the same as we were talking about yesterday also. And although in the rolling sliding tribometer we can measure the friction coefficient is measured, so we know from the test what friction coefficient we can have. And then we see the the variation of shear stress. We saw that the shear stress is developing in the subsurface, and so the blue is the compressive shear stress, and the red is the tensile shear stress. That also we saw through the numerical simulations. Okay, and now the question here is, which direction is the top wheel moving disc? What do you think? We've learned something from the simulations, right? Which direction is it moving? The top one here, clockwise, counterclockwise? Clockwise, the top one. Why? Right. So this becomes a confusion, and we have to be very clear. So again, in this paper, there was a lot of things, why you're not shown the direction. So it's not shown here, but it should be shown, and that is or you make it out with this reasoning actually. But that's, so you can see here that it is shown here now. You can see that this is rotating counterclockwise, as you said, and the front of the top wheel has compressive stress minus shear stress, and the rear part has positive, which is tensile. Okay, and you can see the deformation layer is developing similarly, the second diagram here. So this can be seen on the rolling sliding. Now there are two SRR. What is SRR? Slide to roll ratio. Okay, and there is a that has to be declared how we are doing it. I'll just give you that formula. Slide is the difference in the velocity, surface velocities of that two, right? And roll is, what will roll be? What do you think? Two rollers are moving like this. What will be the roll velocity? Slide is easy. Huh? No, they are different. We are putting in the inputs such that they are different. But what will be the roll velocity? It's taken the average of the surface velocity of the two. So the slide is v1 minus v2. The roll is v1 plus v2 by 2. Okay, so the slide to roll ratio is v1 minus v2 divided by v1 plus v2 average divided by 2. Okay. Yes, this is a 2D model. Yeah. So this is a tribometer actually. We are just trying to study under what slide condition how material deforms. And also, if you see that in many of the studies you change the equivalent, so the simulation of this will be, if you do the analytical model of this, you will convert it into a flat like that. But I am not aware of any tribometer. Maybe is it there in somewhere where you have a rail where you study? It will be a long distance tribometer actually.
Yes, we have one in the lab
Okay.
because it's a vertical machine. We have 5 meter of diameter,
Hmm.
and we have a real rail, and we put almost not a real wheel, but something which is very very similar. And this is not a full scale tribometer, but the size and the material are very close to what you have already.
Right.
It is not in the building itself. It's
Yeah, but circular, be careful because there are other forces which will act, right? So yes, they may. You have curves on the tracks also where the flange hits the track, but whether we want to do that or not. So in tribology, you may not have everything for experiment. So this is one case. This is one of the many cases where you have to really do a thought experiment as to how this is similar to your actual one, and there may be conditions where it is not. You have to state that, right? And then maybe if you get more money, you make a big tribometer or a better tribometer, right? So this is although this tribometer, I think it is there. This is a made in United Kingdom. I think is it there in Leon, this Plint?
yes, we have one
Yeah.
machine, but not a clean one.
Oh, acha, not a Plint. Okay. So it is there in Leeds, I think. University of Leeds and Southampton, and one in Japan, and one in Germany, and Tata Steel, and we have it now. So if you go through the website of this company, you will see 4 or 5 places in which IIT Patna is there. So we have these stresses, and because of sliding, we saw what was happening because of sliding. The symmetry of the subsurface shear stress was changing, right? So this is shown here also. You can see this is 0% sliding, it's pure rolling. This is 5% sliding, and you can see that this is more the tensile with respect to the compressive. Okay. So this symmetry which we were seeing in the simulations, this is also simulation just now, very difficult for us to see in the experiment. Okay. But this is an abacus modeling we've done. So this also shows the symmetry which is there at symmetry is not there at 5% blue, and symmetry is there in red, which is 0%. Now what we see from this is that there is what is called ratcheting happening when you include slide. Okay, this is the accumulation of the plastic stress which goes on increasing like this red if you have sliding, and if there is no sliding, this ratcheting doesn't happen. It's called plastic shakedown. So this is one takeaway from this study we've done. Okay. Now there are correlations to this in the experiment. I'll show you in terms of how the cracks have formed, how the failure has happened, but this is what is we are getting from this. So this is the important conclusion from this study, which is a simulation abacus modeling. Now we start with 2 studies we've done for the same model, but on the experiment on the tribometer. Okay. And there is now boundary lubricated. We as I told you, this is 0% and 5% sliding here, 2% SRR in this, and we put as little oil as possible, calculated the the ratio to find out lambda for boundary lubrication, measured the surface roughness, and done that. Now as we know, the material is paralytic. So there is pro-eutectoid ferrite here, and you'll see this that this is how the cracks start because of bending of paralite and squeezing of this ferrite, and the cracks start from the grain boundary. So I think now rail systems all over the world, I don't know how it is outside, but they are trying to change over from this steel paralite to, because of one of the reasons being the kind of failure which is we are seeing in this, and it is happening on the tracks also. So this is the if you see the figure of the tribometer, there are 2 rollers here, just like in the abacus model. There is a pneumatic kind of a piston here which is pushing it down to different forces, and we cut this and measure the the surface at 3 points and the subsurface also along these planes. And as I said, there is different surface velocities. So, we find out the slide to roll ratio as I told you. Now, what we see here is that there is the bending of the parallite, and if the slide happens, if the slide ratio is higher, this starts cracking, and you will get lot of cracks coming up to the surface. Okay. And so, the roll-in direction is like this. The the cracks will form like this, which we will see very soon, and you start having micropits forming, fatigue cracks. We will see the details of these pictures, more pictures now. So, just to get you into this, probably I should have told you before, but this is the lambda ratio we maintain, 0.467 for boundary lubrication. This is the maximum pressure, Hertzian pressure we have, SRR of 2 and 0%. So, this is how what are the conditions under which we have done the test, and these tests take a long time. The other thing we have tried to measure is the surface topography parameters before and after the test. So, what are the surface topography parameters? Skewness, kurtosis of the surface roughness, then autocorrelation length. We are talking about 3D surface roughness here now. You see, it is not RA, it is not RQ, it is SQ, SA. So, these are 3D surface which we have more work done. Harsh is also working on that. We are trying to work out, trying to understand how the surface, how the statistical distribution of the surface changes with time. So, this is a part of that work. We are, part of this work is that trying to understand how the statistical distribution changes with time. So, you will see now a little bit here that before test we have a skewness of 0.081, after test it has increased. Okay. Everything increases actually, 0.0717, 3, 0.256. Now, the pressure is changed here. Okay. This is a different pressure. Then look at autocorrelation length. The autocorrelation length is the, any idea? No. So, this is now when you study surface topography, it is very interesting. The terms in that is what you use in dynamics. So, for me it is slightly easy because I also work in dynamics. Autocorrelation length is used in stochastic vibrations. Okay. It is nothing. If you have a signal which has which may be not a very deterministic signal, the autocorrelation is you copy paste the signal, you will have 0 very high autocorrelation, because same it will, now you move it by a certain shift tau. Okay. So, you will go out of phase, right. So, when you put a sine wave on sine wave and start shifting, you will get a cos wave after that. You see that? So, the autocorrelation of a sine wave is a cos wave. Now, we are not talking of sine and cos, there are so many frequencies in a surface roughness. So, when you shift it for a random surface, it will never come back. You see, it is not a sine wave. So, the autocorrelation goes down very quickly. It is like an exponential curve. For a random surface, it goes down. For surface which has some correlation, maybe because of lay or the way you are machining it, EDM produces completely random surface. But if you turn, you grind, you will get some amount of correlation. Those go down very slowly. And random surface, so if it is decreasing a lot, means you are creating a random surface. So, here what is happening, autocorrelation length, of course, there is a definition to autocorrelation length, 10% of the original value under watt length, right. So, that is the 0.045 becomes 0.0108, it increases. You see that? What does that mean? A random surface is becoming correlated because of rolling sliding. So the whole process, the rolling of a wheel on a track is like machining also. It is changing the surface topography where is happening. So now because it is going in a determined direction, straight direction, it is putting a correlation between the two surfaces of the parts. This is what this is telling us. So this is very interesting, how the surface changes over n number of cycles. And this also gives us that. You can see the change in, now this is a power spectral density, again a term which comes from signal analysis. This is not Fourier transform. Square of the amplitude of Fourier transform gives you the power spectral density. The phase is gone. It's a scalar, right? But it gives us a very good, because it's a 3D surface, in different directions, what are the frequencies in the surface roughness. So initially it is, you can see it is very directed because of the machining. Grinding has been done on these discs. But as it starts going, running, we see that you see other frequencies coming in the directions. At 2 GPa, this becomes even higher actually. Okay. So you have more frequencies coming in different directions of the surface. So if you see the surface, the crack in the rolling direction, these are seashell shaped spalls which are created, and these join up and make pits and micro pits. The one important thing which I got from the previous lectures was that there can be cracks generated from the surface, and there can be cracks generated from subsurface, right? So cracks generated from the surface are basically being formed because of the surface roughness. And of course, we've had a long discussion on this. Cracks formed under the surface of many reasons. It can be inclusions, it can be grain boundary, we'll see that. And they can join up those cracks, and then you'll get a big pit, spalling will start happening. So these are the kind of cracks which we are seeing here. And if you see the subsurface, this image which you are seeing in the center is before the test is run, and after the test is run, you see that the perlite is bending, which I showed you before also, and for very high slide to roll ratio, it starts cracking, and the cracks are created along this bending of the perlite. Okay. And the hardness also changes because of this, because the ratcheting is happening. So the hardness at the surface also changes. So we measured the hardness as it changes by about 20%. So now, so this is one test. We had 0% and 2% SRR. Now this is that extreme test we did with 20% SRR, and very difficult test to do because the tribometer is to shut down. If you try to do with under boundary lubrication, there was so much of vibration. It has this thing trip with a vibration. Accelerometer is there. If the vibration goes too much, it shuts down. So with 20%, we had a lot of issues, but we used to stop it, run it again, stop it, run it. So and then we saw that lot more. Obviously, as we can see, that bending of the perlite is going to be very, very strong here. So I will not, I'll just show you the full dry test. As you can see, the dry followed by, so we did fully lubricated RCF test, fully dry RCF test, dry followed by lubrication, and dry and lubrication in an alternative way. So lubrication is the oil, not water. Okay, this is a oil we have, and I think the viscosity is how much? The viscosity we are using? ISO-VG30, base oil, mineral base oil. Yeah. So in this, you can see that the crack formation is very, very strong here. You can see, and at a very shallow angle, 13 degrees, you are getting for fully dry test. For dry followed by lubrication, you can see this angle of the crack at about 28 degrees. Okay, dry and lubrication in an alternative way at about 35 degrees, you see, and fully lubricated for the time we ran this test, and these are long term tests on this tribometer, by the way. This runs 24 hours, sometimes 5 days at a stretch. because we are looking at 1 million cycle. I'm sure the RCF, same thing is happening here everywhere actually. These tests take time. So you have to have some automatic control in this. So if a person is not there, it should either shut down or the reading should be saved. You should not lose data of 1 or 2 days. You have to program it like that. So now what we understand is that as this contact moves forward, you start pressing this crack, okay, if there is a small crack which has been formed, and as you reach the edge of it, you create a mode 2 kind of, because this will be pressed down, this will be pressed up, so the at this tip the crack will be almost mode 2. Okay, now this is something which many of us can pick up and do some more work. A lot of it has already been done also, but we can use it in our models. And then when it rolls over the crack, especially for lubricated or tracks having water or liquid in it, because of the hydrostatic pressure of this liquid, it gives you a mode 1. It creates a hydrostatic pressure, and so that this crack will now propagate because of the hydrostatic pressure. So this is a problem with rain on where rail tracks. You will have this crack propagating because of this also. So to prevent this, what are the solutions? So that is the important thing, because we were in touch with Indian Railways on this. So I'll tell you about that. And this is the kind of wear which is happening, as you can see. The rolling direction is like this. The wear for these are the cases of dry lubrication. You can see a very high amount of wear. Now how did we get the wear? We measured it, the profile of the track, we just measured it. Okay. Okay. So obviously what is happening is, one thing which I wanted to show you here is, I should mention, because this is the kind of solution which is there. Obviously we know that people are saying that it should be here. Where did it go? The cracks are forming because of these inclusions there. Okay. So you can see the cracks forming here. I just wanted to show you, where is that picture? What it tells you is that actually this ferrite is softer than perlite. So perlite is cracking up, but it is also squeezing the ferrite. So there now starts happening the crack generation at the boundary. You see, so can we have rails without ferrite? Right. One is this, to reduce this, because otherwise this is a serious thing. For we are trying to increase speeds also now. Although the correlation of speed to the slide to roll ratio is something we have to see. If we are going at a higher speed, to how much is the SRR which we can put on a tribometer. Again, coming back to the question, not everything can be as it is. It's difficult for us. So tribometer conditions have to be very carefully thought of. You have to really do a study on simulation study of the real case, which is the wheel running on the track, and see how much of slide to roll ratio there is for higher speeds. Now that will get us to what previously in the last lecture a little bit was referred to by Professor Nilias on the Calker theory. I'm not covering that. It's a big theory, and Professor Nilias said it's there. So the the correlation between the speed, the linear speed of the axle to the SRR, which then you will input in your tribometer. So we've done it for 3 cases now, 0, in fact for 0, 2%, 5% and 20%. But where are we for low speeds, where are we for high speeds? I don't have that data at this point of time. Okay. So that said, then we also did some molecular dynamic study also. Sudhanshu has done this PhD, just to understand how at the nano level friction is being created. Now there are two ways of doing it. There's an experiment possible in this with a AFM. We haven't done that. This is a molecular dynamics study we've done, where we've taken, we are trying to see the movement of dislocation, which many people have reported also. Okay, and asperities would probably collide with each other, and then each asperity is made up of number of atoms. So we could do to the extent possible. It takes a long time, as you can understand. Each asperity of nanometer size has hundreds and thousands of atoms. But in this simulation, we are taking each atom, one atom, and finding out the forces between the two asperities. Now, if the two surfaces are of different material, so we've taken iron and copper. So it can be iron on iron, copper on copper, or iron on copper. Okay. Now, iron on copper is metallurgically incompatible, right? So you know what metallurgical incompatibility means by Rabinowitz criteria. So in general, at a macro scale, they don't scuff, they don't seize, the two they won't weld in each other. So that is coming out here. That is coming out here. Also, we've tried to correlate the basic laws which we use at macro scale and done a plot, which I'll just show you at the end, which is like Hamilton's law and Archer's Ware law. At this scale, at the nano scale, how it follows, whether it is valid or not. So there is some indication to that also. So we know that these are, if we've taken this from a reference, by the way, for UNCD, ultra nanocrystalline diamond, if you see the surface here at 2 nanometer scale, then you are able to see the surface roughness, which is not very different from the surface roughness you see in macro scale or micro scale also. Okay. So now this has to be modeled at this scale. So what has been used here is an open software called LAMPS. There is a way of doing it, in terms of now there are certain properties in this which have to be, which are different and which we don't use in our normal macro scale. The van der Waals forces, they come into effect here now. You see that? So there is a between two different materials. Now if you're there is no oil in this, it's a simulation only, but trying to find out how much is the van der Waals forces between copper and iron, iron and iron, copper and copper. So those things have to be input. Some of it we don't know, we get it from literature. It will be difficult to measure experimentally on that. So you see, this is the case where we done iron on copper, radius of 70 nanometers, asperity. We have number of atoms, you can see it is in some 84,000. Number on the lower asperity, also of the same magnitude. The interference level, okay, you can see one asperity is going to collide with the other. So this delta is the interference level. Then time step, we take a time step of picoseconds, okay, and initial temperature, we do this. Now same for copper and copper, and iron and iron. So you can see this is all pure metals. Okay. The second thing is there is no oxides forming, we are not taking that. There is no oil, there is no dirt, right? So what do you think the coefficient of friction will be in this? Any idea, ballpark value? Huh? Yeah, yeah, right. What you get in vacuum, in space you get that, right? Yeah. You go more than one, that is what we are getting. So it also tells you that if you try to map it to our actual conditions, we are not very close to that. There is a lot more work to be done in this, but it does give you an indication on certain things. So if you see this, as I said, iron to copper is 1.525 mu. Copper to copper, same metal, compatibility high, 2.79. Iron to iron, 4.9. Okay. Now you can see that copper is copper to copper here. As it passes through, you have, because of very high compatibility, atoms are torn off from one asperity and transferred to the other asperity. Okay. You can see here the complete shape of the. So this kind of copper and copper and this process is going to change surface roughness very radically. We know that. Under scuffing or seizing, it's going to change. So we've got an indication, we've done that also, as to how surface roughness has changed in this study. Now, this is another work where we have non-Gaussian copper rough surface only. Okay. So, in this case you can see we have created the whole slab. In this, now you can see this is a 3D modeling, it took a long time. This is the case where we are trying to see the change in surface roughness. Okay. Similar things you can see, the number of atoms in the top, bottom, dimensionless spacing. Okay. And then the results of this, I am not going into too many details in this, is the average friction force for RMS value of 0.23, which is the black, is higher than when it is the average roughness value is 0.56. Why do you think that is happening? Well, when the average roughness value is less, means it is smooth. Right, more contact is there. It's very simple. Yeah, you're right. Which happens in macro scale also. If you have very smooth surfaces, and you can clean it up and all, which is done, it can be very high, the coefficient of friction. Then you have, depending on normal force. So the friction force and normal force, as per our law, should be, yeah, it should be linear. So for cases it is linear, but then for certain cases it does go non-linear also here. Okay. And this is the Archer's ware model which we have compared. So again, it is close but not there. This is not linear. So Archer, although Archer, if you see his 1955 paper, he does go into asperity on asperity, he does go into that level when there was no molecular dynamics simulation and there was no AFM at that point of time. So it is close to that, but not there. So at this scale, obviously under these idealized conditions, the law is followed, but it is not exactly that. So more amount of study required. Where is it required actually? For MEMS and NEMS devices, right? For macro, we are already doing it. The best we can do is AFM, SEM we already do for characterization. So, so these are the conclusions basically in this. So that's one thing, and this was part of project also. The other is, quickly I'll just try to show you some fretting studies we did on again a PhD. In fact, it is by Krishnamurthy, who's there online. He's in this class actually. So we've done a study of basically, I'll show you the materials. This is basically a definition. I'll come to that. Same, I don't want to go because we've learnt about it a lot in the last 4 days. This is what we've used. We have not made our own tribometer. Okay, we should do that. That's a good thing actually, but we've not done it. We are using this Artec, and this is basically, plate is moving. There is a pin with a hemispherical tip, and there is a way to measure the displacement. The specification, the normal load can be between 5 to 100, tangential load, stroke and frequency. So now, as I understand, of course, obviously characterization things are there with us. So this is our what we've learned from the last 4 days also. I'm just putting it in one slide in a very basically fretting. What I understand from fretting is that the amplitude is so small that it is smaller than the diameter of the contact. Is that right, Professor Nilias? It should be smaller. Okay. If you go to an amplitude which is higher than then it becomes oscillatory wear. Okay. In this case, what we are doing is, we have a Inconel and Zircaloy, and this pair, by the way, has a very important application. It's not a random pair. It's used in the nuclear industry. Okay. And there is a problem because it holds certain beryllium rods, and there's a problem because the reactor has a lot of vibrations. So we've chosen this. They are expensive metals, as you can see, and also not easy to get. So for every time you buy it, they record who's using it for what. Although this has not been funded by any nuclear agency, at this point of time I didn't do it. This is funded by the Ministry of Education only. through the your research scholar stipend grant and all the other things. So in this case now we have made these samples. This is an expensive thing, so we may try to make as much as possible from what we have. We have made, for example, these 9 samples from one part or plate of zircaloy. We made Inconel, turned it into with 6 dia, and then there was a solution to this also. At the end of this work, how can you reduce the wear? How can you reduce fretting? So we tried out titanium nitride coating. So there are 2 parts to this. One is understanding fretting, the other is solution to reducing it. So the subsurface characterization, there are steps to this actually. We have to take each of these samples, do section them out, do diamond cutting, micro milling, then doing indenting, surface, and then SEM. Okay. So wear volume is estimated by finding out the depth and the area, and this is done very commonly. We put it in MATLAB. Optical profiler, we have optical profilometer in situ in this tribometer. Volume is average height into the area of the scar. There is a finite element simulation also, which Krishnamurthy has done in this. Again abacus, and some amount of crack and all this was done. So again you can see which has been there's a very fine meshing which has been done at the contact. So what we find is that there are 3 stages to fretting from the experimental. And in the first stage, the surfaces in close contact, metal to metal between 2 surfaces stabilized, plastic deformation of asperities. Adhesion is so adhesion is happening at this stage. Okay. So this study was an attempt to draw a wear map in time, understand with time whether these stick and slip zones change and how they change over time. So stage 2 is formation of crack at the outer boundary due to plastic strain. So the outer boundary of the stick region, which is a circle, you can see this here at the center, this is sticking here, and these cracks start forming, and the cyclic nature of loading is a responsible factor. So the cyclic, it removes that. So it is very easy to understand that the center part is sticking and you are moving it, very small amplitude. So what will happen to the part outside that? It is going to detach from there. So you will start getting cracks. This is what we understood, and from the experimental we see. And this now over time, this region of because of the cracks forming, this stick actually starts becoming slight. And finally we see what we've learned in the last 4 days is it completely slides, gross sliding, where this circle is complete. You will see in the pictures it becomes a so stage 3, that's stage 3. Now there is a lot of oxide being formed. Generally oxides are hard, so they will create abrasion also, right. So mechanical loading and high surface energy is the key factor for oxidation. There's temperature there, right. So oxidation is happening. There is debris being generated, and the rupture of the transferred material due to shear failure and the further oxidation. So we've seen this from the characterization of how much amount of oxygen in the stick zone, slip zone, we can see that. And then the worn surface topography, the interesting thing is this is the pin and this is the plate, the zircaloy plate, Inconel pin. It's like a mating part, it's like completely negative of this. So you can see at the edge of the stick there are deep protrusions in the pin, and there are deep valleys at the same point in the. So these things actually go and create a negative of the hole on the, which makes sense, but you can see that how much of damage it will happen and where it is happening at the edge here. And these are the cracks in the SEM. You can see what's happening after 30 minutes, 60 minutes and 120 minutes. You can see the cracks and the size of this increasing. This is the slip zone in between, 50 microns of. So I should tell you the contact area, if we just calculate, was about 240 microns dia. 120 microns. Our amplitude peak to peak maximum is 45 microns. You see, so it is much smaller than the contact area which we've estimated from Hertzian contact theory. And you can see now, by the way, there are other materials also which have been tested in this, just because this is partially compatible. Zircaloy with Inconel is partially. Now 9Cr1MO steel with titanium 6Al4V is compatible, right? It is compatible. So we wanted to see what is the difference between partially compatible and compatible pairs of material. Okay. So this basically forms, if you take all the pictures we've seen, how the stick zone here, the slip zone here increases, the stick zone is going down, and also in this you see that the zirconium particles are being collected at the center. Okay, and the nickel particles being formed. So the one is the pin and this is the plate. Okay. So this is the FE modeling we've done, which is abacus. We see the very high stresses at the edge, which are the cracks, where the cracks are forming. We've seen in the surface characterization, we can see that. Now the other thing is coefficient of friction. So what we are trying to find out is the transition from from sticking to complete sliding. So how will we know when it is there? So one is, obviously you can't characterize everything. One is the change in coefficient of friction. It reduces when it is sticking to complete sliding. The mean coefficient of friction actually goes down. So that is an indication a little bit, because that change is not very high. If you can measure that small change, then it will give you an indication. So the identification of you can see this change in coefficient of friction, the mean. Once this is this is where the transition is happening. Now, of course, there is more work which has been done on this. It's reported in the paper. You can see in this paper, this is a Tribology International paper. We've also found out the energy within the for sliding, for tangential force versus relative displacement, okay, for different conditions where we change the load, keep the displacement as same peak to peak, and in the other case we keep the other test the load as same and change the peak to peak displacement. Okay. And you can see that the energy dissipated for the tangential force with the change in load reduces with normal load. You increase normal load, the energy dissipated reduces. So if you are trying to find out the damping or something like that, this is a good indicator of that. Okay. And with slip amplitude, as it increases, energy increases, more heating is going to happen as the slip amplitude increases. Now friction and wear, this is the same thing. You can see the coefficient of friction. This is the solution now. We tried this titanium nitride. So you can see the titanium nitride coated friction is 1, okay, uncoated is, so the friction increases, by the way. And when you see this amount of wear volume, okay, so it's very interesting. Friction is increasing, wear is going down. Okay, friction has increased by putting titanium nitride, but the wear is going down. And then you can see these pictures where you can have with titanium coated tin coated zircaloy plate with Inconel pin. This is the pictures after 1 minute, 15 minutes, 1 minute, 15 minutes, 300 minutes, 540 minutes after the test. How it changes, both all of them are going into sliding at the end, you can see, but the titanium nitride coat actually it reduces it is increase the time. If you see there at 120 130 minutes we had complete sliding. In this we are going to 540 minutes. But there is obviously one of the problems is the material transfer. The debris being created, titanium nitride itself is a hard debris. So you have to be careful. That's what my understanding with coatings is, that they may reduce, they may show reduced wear here, but over time they will produce debris. So at one point of time we worked on wind turbine gearboxes. So we found it is better to have soft coating. So we were putting silver. It increased the life. It didn't make it too much, but it increased the life. You see that? We were always afraid if you put tin or DLC, if this thing, if it comes out, there will be a problem. It will create a lot of wear. So you can see the subsurface damage with titanium nitride. This is much clearer here. This is that coating here. You can see the cracks being formed, and this is a complete. This is how it has collapsed. This thing, the cracks. This is much less actually. If you know the plots we saw without titanium nitride, but then titanium nitride itself also creates these pieces which can come off. So I think that's I've finished exactly at 10:30. So this is what we have. There are more things on this. There are papers on this. If you want, we can look at that later. But if you have some questions, I can
Regarding the test you did on those railway tracks,
railway track material.
material. Sir, in that you did like dry test and then you did lubricating alternated. So what was the frequency in which, like, what was the interval when you did like first dry and then after lubrication and that alternate?
That time is there. I think it is. We kept about an hour or so like this. Yeah.
Like, was there any condition like
For the completely dry, it is very difficult to run it for a long time. The trivometer was shutting down. So once it is shut down, then we used to go to lubricated, little bit of lubrication.
so like was there any condition did you measure like in between the when you did first dry and then lubrication? Did you at any point measure like after dry was with the, like after that duration whether any crack was initiated and also
That
was
is
there any
that is there, not shown here, but I think we did something close to that. Yeah, but these are not simple tests. Let me tell you, because you have to take the discs out. You change the experimental condition. You have to put it in a profiler. There is no in situ profilometer in this rig. So if you can get some in situ, or maybe I'm sure I was. I mean, there is some. I think you have a rig, Professor Nilias, where you can do for rolling sliding in situ measurements.
Not really.
No, not there. Yeah, it is difficult. I think case one was talking about one. I don't know where, in Japan or somewhere. That's what I remember. Yeah. So there's a difficulty. We have been trying to do many things, but we've not been very successful. In this, that in situ. Whereas in the fretting, that yeah, it has a. You can just move it, and the profilometer is there, and it's a plate. So it was slightly easy to do that.
so this fretting any same material is done? I mean,
No, same material we haven't done. No. As I said, there was a focus on some application, and there was just one or two papers on this before. But we did have some informal talks with the nuclear energy, agency, BARC. They said, yes, this is a problem, but the way BARC works is after you've done everything, then you go to them for a proposal. So, right, we are trying to still go to them, but they, so we've done this. There's at least two papers on this now.
so in molecular dynamic simulation that you have shown, in that what is how is the coefficient of friction being calculated?
It will give you the force.
One could be shear stress by contact pressure as Professor Milias has explained. Also, how the adhesion is being taken care of when it comes to coefficient of friction, because adhesion is also playing that role.
Yeah, yeah, it is very important. Yes.
Do you, can you explain how is that being?
So, I mean, just imagine you are trying to model two atoms approaching each other, right? So, when they approach each other, there is a force which will attract them, and then when you, so obviously there is an attractive force, the Van der Waals curve, and when you take it off, those forces for number of atoms at different distances all taken together will give you the friction force. Now that there is a question, there is a point to a question on how you will determine that how many number of atoms are transferred to the other side. That is more important question. I don't have that answer. Okay, maybe I should look into that. But maybe Sudhanshu knows.
So for
Yeah, yeah, but how do you get tractive force is what he's asking. How do you estimate tractive force, right? Yeah, it is the van der Waals forces here. It is basically van der Waals forces which is determining that. But there is more to it. I'm not, I don't have that. But maybe you can, if you really want, you can talk to Sudhanshu actually. So,
Maybe I have a few comments and one
yeah.
point regarding the footing wear between Zirkalog and Inconel 600.
Yes, yes.
In fact, you said that there is some vibration within the nuclear reactor.
Yes.
In the application, the Zirkalog is used to maintain the uranium elements, and the vibration, in fact, is due to the formation of bubble into the water.
Mm.
And it's just very localized to the contact between the rod and the maintainer parts. And I would like to go back to what you presented at the beginning about railway contacts, and I have
Oh, rail
few comments
contact.
about that.
Okay.
Maybe the main one is about the rolling direction.
Yes.
We have to be very careful about that because, in fact, there is two things behind this name.
Yes.
It can be the direction of the velocity of the surface, or it can be the direction of the load movement. And the surface and the load movement are in opposite direction. Then we have to be very careful about that. For example, on the left, you can see the two discs. Okay,
Yes.
the rotation of the disc. In fact, the rolling speed is along the positive x direction to the right, but the load movement will be in the opposite.
Load movement is friction force?
No, load movement is a way the, for example, if you have when the wheel is rolling on a rail,
Right.
the rail is fixed, then the wheel is rolling, then you can see the load direction, the loading direction,
Right.
or the load movement.
Right.
But locally, the rolling speed is in the opposite direction. Then I don't know what you use, but okay, you have to be careful about that. Maybe to make a definition at the beginning to be sure that when you speak about rolling direction, is not the load movement direction, or it is, because sometimes in the literature there is some confusion. And,
True, true. I understand what you're saying. It is the case of, just like a wheel rolling on a road.
yes, yes.
Yeah, 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 yeah.
Then, because also I have seen many pictures, you indicated, you have seen some tracks very often,
Hmm.
and each time you indicate the rolling direction.
Yes, yes,
And
yes.
for the cracks, for example, this is mostly due to the friction direction. Then, if you put rolling direction, it will be good also to indicate the friction direction.
Yeah.
Because you are looking at the railway material, the friction direction should be in the same way. It should be the same than the rolling direction.
Right.
Then you have to to define that
Yeah,
properly.
actually, there is a complication there. You're right. That has to be taken into account. For example, the friction direction for a driving wheel is different from that of a driven wheel. So, a locomotive wheel will have a different friction direction as compared to a bogie wheel where no power torque is right. So, we have to make a distinction between this is a locomotive wheel, it is a driving wheel.
Yes, yes.
Yeah, yeah, yeah. I understand your point completely, and how this translates here, if you're saying that is, so let us say both are rolling as it is shown here, and now one will have a lower velocity because you are trying to generate a slip, right? Slide. So the one which is slower will be pulled in the direction of the rolling, right. So friction force on that will be acting along that. For the wheel which is faster will be dragged. So the friction force for that will be right, will be in the opposite direction to rolling. That is what you are exactly saying, right?
Yes, yes, yes.
Yeah. And that translates to a real wheel where you have to see whether it's a driving wheel or a driven wheel. When you apply a torque, you can do a free body diagram of a wheel. Torque has to be changed into force. Then a counter friction force will be in the direction of the motion of the locomotive actually. This is very interesting. Or even a car tire, right sir?
Yes, yes. And if you have a gear contact,
Yes.
In fact, within the same contact, you will have the opposite because below I don't remember the name, below the
Pitch point.
above the
Mm-hmm.
bottom of the dent wall.
There it is very well defined that at the dedendum, start of the dedendum, you will have 100% slide, and it linearly reduces to 0% at the pitch point, and then it again goes up to
And when you observe the cracks on both the pinion and the gear, you will see they are opposite.
opposite direction.
And maybe another small point. When you speak about shear stress, I think it's better. There is no tensile or compressive stress. In fact, it's a shear in one direction or in the other one direction. It's not really compressive or tensile stress compared to normal stress. For the normal stress, we can say that it is a tensile or compressive, but not for shear. I don't use this term. And my last question is about.
But you also used in your, I saw, negative shear force? No.
Yes, but it is just because you have one direction. In fact, it's the same.
It's in the plane.
Just
It's in the
change
plane only. It's normal, not normal to the plane, so that it is compressive or tensile. So normal to the plane, so that is.
So in this case, yes, you are right. For example, here, or the rolling sliding case as we were discussing, when they move, you will see the friction force will act on the, it will try to pull the material in one direction. So opposite to that will be pulled, but on where it is on that side, it will be compressed. This is all we are trying to show here actually.
In fact, you can plot in pure rolling. If you plot a profile of the shear stress, it will be symmetric, anti-symmetric. It will can be, for example, positive, 0, negative to be symmetric, anti-symmetric. Yes.
But in pure rolling, you are saying it is symmetric here for pure rolling.
Yes. And if there is no plasticity, if it is only elastic, normally, if you have friction, you have just a shift of the mean value, and it remains anti-symmetric, but with a shift.
Right. Okay.
And but because you have plasticity, maybe it's different. And I just would like to know, when you speak about bending of pyrolytic materials, is it due to the load movement or to the friction direction?
No,
In
it
your
is because of friction.
okay.
It is because of friction.
Okay, then this is why when you put the rolling direction, the friction direction in your
Should be shown, yeah.
is always in the same direction.
Yes, in this case, yes. But I see, now I see your point. That has to be clarified. Where is the friction direction and where is the, yeah. Okay. So we can, I think, let us do this quickly. Dr. Sharma also has to, thank you.